This lecture introduces the method of undetermined coefficient, a method that helps us find general solution to some of the second order non-homogeneous differential equations. Again, just some of them, not all of them, using this method. So the main advantage of this method is a straightforward method to execute when the assumption is made about the form of big of yt. Again, big Y of t is a specific function to the non-homogeneous equation. Okay, but it has its own limitation. So its one of its limitations is it's useful primarily for equation that we can write down correct form of the particular solutions in advance. So we can write out the correct form for the big Y of t, then we can use this method. So for this reason, it's only used for problems that the homogeneous equations has only constant coefficients, because we need to find out the solution to the homogeneous equations, and we learn to find those solutions when the equations has constant coefficients, right? And the non-homogeneous term is restricted to a very relatively small classes of a function. So it's very limited in terms of what functions of the non-homogeneous term that we can use this method to solve. Right. First, the homogeneous equations gotta be constant coefficients equations. Second, the non-homogeneous term, which is g of t, is restricted to a very small class of functions. All right, so in this lecture, I'll introduce the first case of the non-homogeneous function. So again, the non-homogeneous term is restricted to a small class of functions, and the first class it's gotta be just a polynomial functions. What does that mean? That means the g of t, which is the functions on the non-homogeneous term, is one of the cases that we can use this method is the g of t, it is a polynomial functions at the nth degree. Okay. Just a reminder, what is g of t? So we have the second order differential equation, right, in terms of y and y double prime plus by prime plus cy equals to g of t. So g of t here is just a polynomial. And then if we have a function in this form, then we can guess a form for its non-homogeneous part, y of t. And big Y of t is a specific solution to the non-homogeneous equation. Okay. So the y of t will be in the form t to the s times a polynomial functions with undetermined coefficients a0, a1, and an. Okay. Where n is the degree of p of n. So p of n is the polynomial functions at nth degree, and in the specific solutions form here, n is actually the same degree as the p of n in g of t. Okay, and t of s. What is t of s? How can you determine s? So s is an unknown value at first, but you can determine the value of s. You can determine the value of s by finding the number of times. Number of times 0 is a root of a characteristic equation. Okay, again, s is a number of times 0 is a root of the characteristic equation that you get from this homogeneous equation. Okay. Now, the reason why we're adding the term t to the s is we want to make sure that we have a term t to the s to ensure no term in y of t is the solutions of the corresponding homogeneous equation. Okay. Because if in y of t we have a term that is the same as the solutions of the homogeneous equations, then we're not counting enough solution set for the differential equation. So we always want to add a term t to the s just in case. Again, if your characteristic equation doesn't have 0 as a root, then s gonna be equal to 0, which means t to 0 equals 1. So you get rid of this term if you don't have any root of the characteristic equation to be 0. Well, let's look at the first one example. So if we look at this differential equation here, I want to make sure that the homogeneous parts has all constant coefficient, and the non-homogeneous term is just a polynomial functions with degree of 2, second degree, right? So we know that n equals to 2. So let's do some. N equals to 2, right? And we can find the characteristic polynomial equation is r squared minus r minus 2 equals to 0. And then I can solve for r minus 2, r plus 1 equals to 0. Then r equals to 2 and r equals to -1. Okay, so this is the root of my characteristic polynomials. Do we have any 0 as a root of this equation? No 0 as a root. That means s equals to 0. If s equals to 0, then I know that my equation big Y of t will be in the form t to the 0, it is 1, will be in the form a 0 t to the square, right? Because n is 2 plus a1 t plus an. Okay. This is my guess for the form of the specific solutions to the non-homogeneous part. All right. So now I guess this is the specific form of my specific solutions. Then I can go ahead because it's undetermined coefficients. Now I need to determine what is A0, what is A1, and what is AN. And again, these values are constants. It's constant coefficient. How can I determine these three terms? Let's find, if I know that, if I guess that this is y, then I can find y prime and y double prime. So then I can plug into the original equation in order to determine A0, A1, and AN. So y prime t equals to 2A0t plus A1 plus 0, right? And y double prime t equals to 2A0. All right. Now my goal is I need to plug y prime, y double prime into this equation to find A0, A1, and AN. Here we go. Plugging everything in, I would have 2A0 minus 2A0t plus A1, okay, minus 2A0t squared plus A1t plus AN equals to the right side, which is negative 2t plus 4t squared. Okay, so from here, I will try to combine like term on the right side, on the left side, I only have one terms of t squared, so I put it negative 2a0 t squared. I will have negative, this is t, right? T, I have t here, so I would have negative 2a0 minus 2a1t. So negative for negative, so it should be positive. Okay, and then I have a0, negative a1, and negative 2an. Equals to negative 2t plus 4t squared. Okay, as you can see that now I need to force the two sides equal to each other. I have t squared. The coefficient for t squared is 4. That means negative 2a0 equals to 4. The coefficient for t is negative 2. That means negative 2 a0 plus a1 equals to negative 2. Okay, I don't have any constants, so this whole thing here will be equals to 0. So 2a0 minus a1 minus 2an equals to 0. So let's solve these three equations. This means a0 equals to negative 2. If a0 equals to negative 2, so I would have a1 equals to, this is gonna be just 1, 1, right? a1 equals to 1 minus a0. 1 minus negative 2 is 1 plus 2 is 3. And I have an, so I have an equals to 2a0 minus a1 divided by 2 if I move an to the other side. So then I will have 0 is negative 2, 2 times negative 2 plus minus 3 over 2. So that would give me negative 4, negative 3, negative 7 over 2, which is going to be my an. Okay, so now I have a1, a0, a1, and an. I can plug these three values into my gas. So let's see, yt from here, I can move it up to here. Y of t right now is gonna be a0 is negative 2t squared plus 3t minus 7 over 2 is my big Y of t, okay? Well, and then I need to find the solution based on these two roots right here. I can find the solution to the two homogeneous, to the homogeneous equation from r equals 2, r equals to negative 1. So then I have y of t, I would say y0 of t equals to c1 e to the 2t plus c2 e to the negative t, right? Which is the solution to the homogeneous equation. All right, so now my general solution will be I say little yt equals to y0t plus big Y of t. And simply it's gonna be c1 e to the 2t plus c2 e to the negative t plus minus 2t squared plus 3t minus 7 over 2. This is y of t. Again, you can see that this is the solution to the homogeneous equation, and this is the solution to the non-homogeneous term on the right side, negative 2t plus 4t squared. Okay, so once you have the general solutions, and if you have initial value, you can just plug, first you have to find y prime of t, and then you plug the two initial values into the general solutions in order to find C1 and C2. So let's erase this part a little bit. Now let's find y prime of t, right? Equals to 2c1 e to the 2t minus c2 e to the negative t minus 4t plus 3 is y prime. And if I plug the first value, y0 equals 0 into this, so that you have 0 equals to e to the 0 is 1, so c1 plus c2, 0, 0, negative 7 over 2. Then I have C1 plus C2 minus 7 over 2 equal to 0. Okay, if I plug 0 and 1 into the first derivative, I will have 1 equals to 2C1 minus C2. This is going to be 0 plus 3. So I have now, you see that I have two variables, C1 and C2, and I have two equation, so I can solve for this to find C1 and C2, right? So I would have, so from here, I can say C1 equals to 7 over 2 minus C2, okay? And then I can do substitutions. I can take C1 equals to 2, 7 over 2 minus C2, minus C2, 1 minus 3 equals negative 2. So my goal, I just want to solve for C1 and C2. And at this point, I have this is gone. So I have equals to 7 minus 2 C2 minus 3, 7 minus 3 C2. So that means C2 equals to 7 plus 2 divided by 3 is 3. C2 equals to 3, then C1 equals to 7 over 2 minus 3, which is 1/2. Okay. So I have C1, I have C2. I just need to plug C1 into here and C2 into here to get my general solutions. So my general solution will be, if I erase this right here, I would have, I plug C1 is 1/2, C2 is 3 to be my general solutions. For this equations using the method of undetermined coefficients. And this is an example of how you would use this method to find the solutions for this IVP. Okay. Find homogeneous solutions, non-homogeneous solutions by guessing the particular form of the functions. Find y prime, y double prime, plug into the original equations, force the two sides equals each other to find all the undetermined coefficients. And once you have the specific solutions and a solution to homogeneous equation, combine them together with C1 and C2, and then plug the two initial value to find C1 and C2, and then plug C1 and C2 back into the general solutions. All right, here you go. This is the first type of equation of the functions, right, of the non-homogeneous term. from which you can use this method to solve the differential equation. And the particular functions that we can use is polynomial functions at nth degree.